All right, we'll get started. Hi, I'm Valerie. Today I'm going to talk to you about how to move your team's ETL beyond daily batch processing and enact this paradigm shift of moving into a real-time architecture, including some opinions about how to assess when it's worth it to do so. So more than previous transitions, I think, between different batch processing technologies, say Apache Pig to Spark, changing from batch processing to stream processing is really a paradigm shift in how we think about the core task of data engineering. From transacting primarily with data at rest to transforming data sources in motion or live. Quick intro about me before we get going. I currently work at Netflix, and most of the experiences in this presentation come from my work there. Up until last fall, I worked on the data engineering team responsible for processing pretty huge workloads of data. Data related to Netflix members' playback experience. So you can imagine hundreds of millions of members streaming billions of hours of content. The data workloads this team is responsible for get big really fast. As you can also imagine, the data produced by these pipelines is really important to Netflix to know what's going on with their users. The result is that we've spent years and years implementing various architectures, cutting edge at the time, to process it. So some of these architectures include daily batch, hourly batch, a framework we call Incremental, and most recently, streaming architecture or real-time. The analytics organization at Netflix is very mature, and some of the data sets produced on this team actually go back and impact the product itself, and certainly impact business-critical daily reports, dashboards, and decisions. We basically consider this team's data work to be on a super tight SLA. So as you can imagine, working with a bunch of different technologies over a couple of different architectures at a huge volume and a huge scale, also on a tight SLA, things can get a little bit crazy. So these learnings I'll talk us through today are primarily from that team under those conditions, and my goal is really to help you and your team make a thoughtful and minimally painful departure from the status quo of today, which I consider to be kind of daily batch processing. Okay, so this is a highly simplified view of the world today, what I would consider to be the data engineering realm. So just to state the obvious, the events that you care about are already happening in the wild, somewhere in real time. Whether it's users being converted, making impressions, initiating app interactions, you name it, it's happening all the day long, ideally. The practice of data engineering lives here in the wide, middle, chaotic center, using many more technologies than are pictured here. And unless you're using an incredibly cutting-edge, fully real-time system, in which case I also hope that you are presenting here at Databricks and I can watch your presentation. The overarching logic of batch processing is that at some point between event generation and your process, events are being gradually materialized and stored in hopefully logical units. In the batch world, this is presumed to be happening upstream of you. Your job as a DE in a batch processing framework is to understand how to transport that stabilized data from point A to point B. And you also have some know-how about how to make sure it's accurate, how to join it, if there will be late arriving data, the cadence of upstream dependencies, et cetera. Lastly, if you've been doing this a while, your organization probably has robust orchestration tooling in the form of audits, readiness signals, ability to rerun your job safely or idempotency, along with considerable know-how that you've built up along the way. In short, you have a bunch of tools, processes, and infrastructure which will not work at all in the event streaming context. What's more, your highly skilled team of DEs are very used to using the existing system. Put another way, you have the potential for some really negative sociotechnical outcomes. And I think this is a lens that's really important that we talk about in operations specifically. There is not an organization I've ever been a part of in which the tech and the social are actually inextricable from each other. Your business impacting outcomes depend on both the tech you use and your team's practices using it. And when I say transitioning your batch pipelines to real time could cost you your sanity, it's not due to the technology alone. It's also how we're using it. It's a bit technical. This is kind of the easy one. It's often in the realm of the technical that a conversation about moving to an ultra-low SLA event streaming architecture will even get started. We can do it, so why not do it? So some of the technical considerations we're familiar with, batch or real time. You want to choose efficient and accurate processing. You want to leverage infrastructure well, catch edge cases. Let's think about the social. Social impacts like the following. Odds are you have stakeholders who want and expect to consume your data via a pre-agreed upon mechanism, readiness signal. You have colleagues with whom to share job context, perhaps get on-call support. And ideally, you have audits forged with downstream users to check not only that your data is complete and ready, but also to protect them against data quality issues. So let's think of a sociotechnical bad outcome, which is likely to occur as you transition from batch to real time. So your real-time job continuously built lag overnight, and the on-call person incorrectly published it, and now everyone downstream has processed incorrect data. I genuinely wish it was hard to come up with this example, but in reality, it's one of many that our team has experienced over the years. So wait, I can hear you thinking, Valerie, I can already publish bad data today in batch. This is not a problem distinct to the real-time environment. Would I be likely to do this, or more likely to do this in real time versus batch? My answer to this is, for a while, yes. More than anything, this is what I want to impress upon you today. Transitioning from batch processing to real time requires both the familiar one-time cost of learning a new tech of real-time technology. So that'll include how a watermark works, what your checkpoints are doing. Perhaps you're new to consuming from a real-time source like Kafka. At Netflix, we deal in Flink as our real-time system and Spark as our primary batch system, just for your information. So the longer task to learn, other than the one-time pay down to transition, is learning the conceptual difference of debugging data in motion. Rewiring your mental framework to do the core DE functions without data at rest as your source. A few of these challenges that we'll dig into further are reproducibility of issues becomes extremely challenging in a real-time environment. Time sensitivity becomes extreme, and risk of data loss from the source is likely. Strong potential to create duplicates as you reprocess, which is not a common risk in a batch processing paradigm. These are just a few. It takes time, practice, and a lot of communication to overcome these challenges. And odds are, if you have moved into a real-time architecture for high criticality and low SLA performance, you might not be expecting to spend a ton of those. So knowledge is power, and hopefully this presentation will leave you some usable tidbits to steer you along the way. Just to be scientific, let's restate the paradigms that we're talking about. Okay, classic daily batch pipeline here. A common challenge that we address via daily batch processing and that I've illustrated here is the standard repartitioning from processing time at source, forklifting over into a target table, repartitioning by event hour. This is a hopefully familiar operation. The challenge here, as is kind of identified with the late arriving green data, the challenge here is that any data arriving late is going to miss the batch for the day, need to be restated. It's a long time to wait 2 days for the late arriving data, and it's also a long time to wait for any of the morning's data, which won't be processed for 24 plus hours. Two alternative processes we leverage at Netflix for tighter SLAs, but in a still batch paradigm, are hourly and incremental batch pipelines. Foundationally, they're very similar to daily batch. Hourly jobs run on a fixed configurable interval to process data on a less than daily cadence. Incremental jobs accept a dynamic source volume, so they basically require that you store a watermark to record the last successful timestamp of read from source. This framework is almost a manual version of what real-time architectures offer out of the box, requiring that you store an external metadata point so you can read and reread dynamic range from source. Both of these are good options to remain in batch paradigm, but get data with less latency. They also both require specific job logic and table structure to not duplicate or throw away data, so it's not a free lunch. Contrast this with event streaming framework. So instead of having many jobs that are consistently reading fixed increment of data that you control, configure, you have one, represented here by a giant arrow, application that's continuously consuming event data and continuously writing it out to your target table, publishing it by target partition strategy of your choosing for your analytics use. So what are really the key differences here? And I'm going to compare real time to all of the 3 batch options, and why are they impactful? So processing unbounded state. At the very heart of the difference between the two systems is this fact. Instead of processing deterministic, materialized data stored upstream of you in meaningful chunks, the real-time data processing application is continuously acting on unbounded state of otherwise vanishing data. Again, it's worth a pause to think about how much this impacts our baseline assumptions in batch data processing. The modern data warehouse is already embedded with more or sometimes less obvious systems for us to reason about the contents of any particular table, any particular partition. So unless you're starting from scratch, odds are in your batch jobs, you're transacting new data from a production application into a fairly structured data warehouse. For example, in batch, if I wanted to do analysis about yesterday's data or data from 2 weeks ago, I might query a table that was partitioned by that data against a snapshot of a dimension from the relevant time. We've already embedded our data engineering thinking how to solve some of the problems of change over time that need to be revisited when building a real-time application. In real time, the fact that source data is unbounded, the very fact that gives us the ability to do low latency processing, also is the source of many challenges to using it. So for batch, again, choosing from a relatively fixed state, kind of think of it as a menu from our source, but configuring how much to bite off at a time, a day, an hour, et cetera. Depending on our source characteristics, we might choose to restate multiple days of data if we know there's late arriving, depending on the processing power volume scale. All Spark users know that even in batch, there are state-based tipping points in terms of processing power where if you hit some volume, hit some scale of data on a busy hour or a busy day, your Spark job will fail with out of memory. Similarly, a join may issue skew and fail if suddenly the distribution of keys all moves to one high volume key. In real time, many of the above challenges are still there, still operating in a distributed environment. But you also have dynamic state that is much harder to recover from failure for you and for the app, but we'll talk about that in a second. For example, at high volume, a common scenario is that state will build, called lag, if the app can't keep up with your source. This becomes increasingly less efficient and eventually possibly gridlocked by back pressure, taking down your real-time app. The job is not idempotent, so retries will not deterministically replace the data that you have missed. Once you cross the boundary of a healthy state threshold, the app will come down with out of memory or skew. You can introduce duplicates, as I mentioned before, in the state of app failure or retries, which is also not a risk you encounter in batch. These are only the risks of operating a stateless real-time pipeline. The term state is confusingly overloaded. I just want to acknowledge for the room. So one particularly complex example in a stateful app, say if I wanted to use a real-time app to group app sessions in real time. Say I need an app start, an app end. I want to build a state in my app and say, start plus end equals session, right? So if the app start event arrives into my state, I need to decide how long I should keep it in state and see if the app close event ever arrives. The larger the app state becomes with events waiting for their pairs, the more bloated and resource pressure the app experiences. I'm not going to hold on to this app start forever and just let it build and build in my state. So eventually, I'm going to have to decide some bounded parameter by which to flush it and either throw it away or publish some kind of a partial session. In the real-time app, job logic needs to be designed defensively against unknowns in the state, exactly like this, and that's during normal operations. Contrast with batch, where lateness will guarantee completeness. There's no change to data volume. So in batch, your job is on an assembly line. These questions of how to close a session are less impactful. You're either consuming source, which includes all of the events, or does not. You're not in the position to make the decision of when to throw away the second half of a data set. Finally, a similar use case joining across two streams can have a similar impact to data quality. So say I want to join one stream with late arriving data from another stream. I have the option to hold on to all the early arrivals in my state, accepting the bloat and waiting for the late arrivals to arrive, join, and write. But what if there's a data outage in the upstream system? I could be waiting forever, and I will eventually throw away those data points as they time out, producing facially complete data that is, in fact, a partial representation due to a data outage upstream. Latency versus completeness. When your data looks ready. One of the biggest drivers to adopt a real-time system is obviously the low latency. This perk is real, especially when all the systems are working as expected. One conceptual difference in place, even in normal real-time operations, is in a batch system, your controls for latency and completeness are very coarse. Theoretically, if you could tolerate infinite latency, you could easily achieve 100% completeness. Like, if I didn't need to publish my table on any kind of timeline, I could wait until every single late arriving event made it into the source, publish a few days later. In the real world, of course, we do not tolerate infinite lateness. That's not a reasonable constraint. So instead, there's some usually imperfect cutoff to incrementally consume the source data that we're dealing with and deal with late arriving data eventually, hopefully. In a batch world, you need to know about the latency of arrival to your source, but you hardly have to interact with it after you initially grok the design for your pipeline. Once you set your job configs, it's relatively fixed. A common example in a daily batch, you might consistently report a shortage of the last hour of the day, because you assume you want to process around midnight, but you know that some events arrive as late as 2 a.m. Those data points arrive very latent the next day when you restate the previous day's batch, but totally complete. In real-time pipelines, data is constantly trickling in. This can provide a low latency output if your downstream users want to consume in real time. That's a good model where the handoff, they benefit immediately from the real-time output of your job. There are challenges to remediating that architecture when anything goes wrong, which there are additional, I think, presentations about. I highly recommend looking into them if you're considering real-time to real-time architecture. More often, especially if your current data warehouse is mostly batch, your downstream users want to consume from your job with a batch job. To accommodate that, you're gonna need to draw some arbitrary I'm done line that emits whatever your standard publish signal of choice is. So you'll also have to find a way to replace the equivalent of the blocking audit that exists in the batch world. There is no feasible way to implement that in real time. And just like the structure of the data warehouse has sprung up over many years to facilitate batch implementation, the orchestration tools you can rely on to do those kind of operational things with your real-time pipeline don't exist. So auditing, signaling are likely a bit of a retrofit that you would need to implement to make your real-time system emit signals anyone can use. So this is an example of the trade-off between latency and completeness in one of our real-time systems. We have to communicate with stakeholders saying, if you want to read the most low latency version of the data, the earliest we can reasonably publish it and say emit a published signal, it's only gonna be somewhat complete. This is expected. We are no longer being offset by the buffer window of events accumulating at our upstream source. Instead, by passing them to you in real time, you're only gonna get what we've seen up until that point. Finally, this is a good example of how the breakdown in batch infrastructure to mitigate possible data issues in a real-time pipeline can be very tricky. You can't easily compare some of the tactics that you would use to say this data is good, this data is publishable, this data is of high quality, don't translate easily in the real-time environment. You can't easily compare to the upstream source as one might do in an audit to say, this is done, this has published all of the data. It's hard to impose a blocking audit, as I've mentioned. The best you can often achieve is a sort of very noisy system of real-time alerts, which can nudge someone and say, things are going wrong. We're still publishing the data, but something's going wrong here. Get up and look at it. Finally, there can be holes in the data, which can be very subtle if your app experiences lag to the point that you start losing events from the source. We're gonna talk about this more in a second. If that loss is not as substantial as it would trip an audit, and with no way to look back upstream, you're basically gonna be flying blind about if you have shallow holes in your output data. Okay, real-time data means real-time debugging. So here we're really back to the example from previously when you're paged in the night and on-call person needs to make a good decision. So how is this different than batch? A high-pressure SLA is a high-pressure SLA. I think many in this room have probably experienced the sensation of the ticking clock as you try to unblock a pipeline. The major differences are really that you don't have the fallback of the idempotent job rerun. I would venture many Spark users also have had the experience of tuning and tuning and tuning an hour or a day or a batch until it succeeds. That is not an option to you in a real-time system. My colleagues Shinrin and Sundaram will be presenting next with some in-depth explanation of how we've tried to overcome the challenge of backfilling. But the long story short is that backfilling in real-time architecture is very challenging. And on a purely social note, the knowledge transfer on your team needs to be really strong and very constant, especially as everyone's on a different point in the learning curve of familiarizing themselves from a batch paradigm into a real-time event paradigm. Without upstream data at rests, your jobs basically would have a very tight relationship between processing time and response time. So these are just some images of PagerDuty, which will become a part of your lives if you start using a real-time system. Okay, so final difference between batch and real-time. They have different infrastructure needs. So, the batch jobs share infrastructure and periodically spin out, issue jobs, succeed or fail, have a low threshold to rerunning, reattempting. Real-time jobs require a fleet to run constantly, and for software engineers who are in the data space, perhaps a facially more actually familiar run structure, infrastructure need. So testing changes can be harder. For batch, you can reasonably test out Spark version upgrades, job logic, orchestration, et cetera, by firing off a single day or hour of data, comparing it deterministically to the production version, diff it, you're good. That's a pretty straightforward way to see if your change has had negative impact. In real time, this is very different. So you need to have an application constantly deployed and healthy, and as I mentioned, also be sensitive to the infrastructural region that the application is deployed on. Okay, so what should you do? So the real answer boils down whether you should convert your batch pipelines to real time or lower than daily grain. It is up to your business use case, but I encourage you to really think beyond the technical. Don't just think of the low SLAs, think socially. Think of your team's ability to meet those SLAs and what debugging issues in this framework will realistically look like as you transition and what you will support in the long term. The intermediate team tax to build this enterprise is to build on this experience and know-how, and that happens gradually. So, as you consider what to do, I highly recommend considering a low SLA batch job. The perk of this is remaining in the batch paradigm, but lowering your overall SLA. There is the requirement to make a forward-looking decision about table structure and job logic, so it's not a free lunch. You can't just convert your daily jobs with no effort. But it is a good way to not break this sort of fundamental paradigm your team is used to working in. Finally, optimize for a smooth on-call. If you do end up going the route, deciding to make the conversion, go into real time, normalize up-to-date runbooks. You will be responding to issues, outages at all hours of the day, and you will likely need to manage an on-call shift amongst your teammates who do not own your job logic. You need a low latency way to be in touch, which likely means pager duty, and smooth communication with stakeholders. So normalizing a path in which you're constantly alerting people that, hey, the normal SLA for this real-time job, it's extended, it's 2 hours, we're 3 hours behind. And make testing parameters aggressive, because you cannot block a real-time pipeline. You need to have aggressive auditing that will at least alert you to data quality issues, and then tools in your toolkit to overcome the need to backfill when data is in fact missing or bad.
Are you part of the centralized, like shared IT services team, or are you focused on a specific like business unit, like gaming, right? That's coming up.
Yeah, that's a great question. So the learnings from this, I was actually on the streaming data science and engineering team. So that is a domain-specific vertical, and that is partially a factor of Netflix's scale. So there are infrastructural teams who support managing Spark jobs and the batch infrastructure. There are infrastructure teams who support our Flink deployment technology. And then I would say our teams are the consumers of their work, the customers to their work. So domain specific, but that is also because Netflix is a large company.
So I see that there are challenges for real-time debugging and tuning. So I was wondering if there's any limitation on maybe storing these events and then try to emulate that later on, like for example, for some team to do the tuning or the debugging. Like maybe you cannot solve the incident and you have to mitigate somehow else, but maybe to do some kind of after incident, post-mortem, whatever you want to call it, analysis. If you can recreate the events, maybe you can look into what was going on in the pipeline at the time. So have you explored any of those options, or are there restrictions on why that approach may not be used?
Just so I'm making sure I'm hearing your question. Is your question, are we conducting a post-mortem or have a team practice of kind of looking back when there's failures, or was this, could you
It
restate?
is more like if there's a reason why that approach is not taken, like maybe, I don't know, the events may be too many so they cannot be stored, or like, is there a reason why that approach may not be feasible?
There can be a lot of reasons. I think that's the overarching kind of message to take away is given these constraints with the real-time processing kind of paradigm. There could be many reasons why either a job is specifically failing and its source isn't it's not scaled right, it's not flushing correctly, its state management strategy is wrong. But then I think at Netflix, there is wide adoption of real-time pipelines. So the teams that are on the fence of, does our use case fit a real-time strategy? Should we make this switch? There's kind of a knowledge sharing there that is, I would say, more abstracted than what you're saying about replaying events that cause one specific failure. So the knowledge sharing is a little bit at the team level. I'm not sure if I'm answering your question.
Yeah, I think
okay. Yeah.
Thank you.
Hello. Congrats on your journey. You mentioned that you use Spark for batch processing and Flink for streaming, right? Can you tell more about that choice? And why don't you use other tools like Autoloader or more complete solutions in Databricks?
Why don't we use other solutions than Flink?
Yes.
Yeah, that is a question, I suppose. I joined the team when Flink was already the status quo technology for event streaming and had been kind of proactively invested in by the Netflix infrastructure team. I think at a large organization, you do get into a sort of challenging place where you have to commit to one technology if per the first question, you're going to have an infrastructure team that supports and owns a lot of it. Netflix is a very pro-experimentation with our own tech stack kind of place. So our team has played around with different add-ons on top of Flink, but I would say we haven't experimented with non-Flink streaming engines.
Thank you.
As a quick note on that, Autoloader is actually a file-based ingestion, and then Flink is more of a record at a time ingestion.
Thank you for the presentation. Great content, so appreciate it. One of the questions that I had, you mentioned about watermark and being able to essentially keep track of what data has changed. When one of the platforms that we're building is pulling data from Oracle and a bunch of different systems. And what we're finding as a challenge is keeping track of what the changes were, especially when you get rows that get changes, so it's not necessarily a new primary ID added or anything like that. Any strategies from your experience on how best to pull in just the changes and not the entirety of the table every day, because that's essentially what we try to do?
I think this is a wonderful articulation of sort of the core challenge of data warehousing at scale is that the actual ability to hone down on only changed rows is often more expensive and time-consuming and compute-consuming than just a raw ingest and then kind of offline comparison. I'm not familiar with Oracle. I know that the technology, we're big Iceberg users at Netflix, which I haven't delved that deep into the upsert kind of technology there. I know that that is a future-looking feature there. The founders are former Netflix employees who are great. I recommend looking into it, but I don't have an answer for that problem. It's a big one. Yeah.
Hello, hi. Thanks, nice presentation. Everyone has been following what Netflix does in the data space. It's really amazing. I know you have multiple different platforms, like you have Keystone, you have common log processing, you do data aggregation in your analytics like Tableau layer as well. So how do these platform teams own the responsibility in terms of any data problem like you were talking about in the middle of the night, having a pager duty call, and the domain team kind of addresses it. So how do you distinguish between which team owns what? Because there are so many data hubs and so many different latencies, right? So if you could give little insights, that would be helpful.
It's a good question. It's a very two-way street at Netflix, I would say. So the infrastructure teams maintain an on-call rotation that they are, pageable at any hour of the night, and they also have automated alerting on their own system. So if there is something at the kind of very core Netflix layer, which would impact every Flink job, every Spark job, they would be the recipient of that kind of alert. The job owners, us data engineers who are in our domain-specific regions, writing our own job logic, deploying it, the owners of our own jobs, have our own system of alerting, and it's very team by team kind of what that looks like in terms of if they need overnight support or if you need pager duty, kind of what level of alerting. And then there's many times when like it's a two-way street between the infrastructure team and a specific team that's having job logic errors. That's kind of how the breakdown works right now. There's a high degree of communication between the two, but both are supporting an on-call representative. And then if your job is failing and it's kind of like a you problem in your own domain, your own job design, they will help you, but it's more, they're there for like system-wide issues. Yeah. Okay, I think that we are at time. Thanks, everybody.
Thank you.